Nuclei can get excited, energetically, just like how electrons in atoms move between energy levels by releasing and absorbing photons. The nucleons in a nucleus can change energy levels, except the photons that they emit are gamma rays, and the energy of the photon is equal to the energy loss when dropping to the so-called ground state, meaning different photons for different nuclei. And while excited states usually have half-lives measured in trillions of a second, there are a few metastable states or isomers that can stick around for orders of magnitude longer. One isomer, called tantalum 180M, has an estimated half-life of over 45 quadrillion years, even though its ground state radioactively decays with a half-life of 8 hours. Such isomers may open the door to stable super-heavy elements, or create nuclear batteries with gamma decay that can be turned on or off. And our understanding of excited nuclei has even helped us look for water in our solar system by looking for its parts. It doesn't take too much imagination to detect radioactive elements from space. But to measure non-radioactive elements, we have to be a bit cleverer and collaborate with cosmic rays, high-energy particles from outside the solar system. When a cosmic ray hits a nucleus, it can cause a fast neutron to be ejected. Some of those neutrons will just fly out into space, while others will interact with the nuclei around them. These neutrons can be moderated or slowed down through collisions, and by far the best moderator is hydrogen. But why hydrogen? Why not helium, a perfectly respectable element? Well, it's because hydrogen's lighter. Since these are collisions, momentum is exchanged, and a more massive object doesn't have to move as fast to carry the same amount of momentum, and therefore doesn't steal as much kinetic energy. The classic example is bouncing a bouncy ball against a basketball, or a bowling ball, or a really, really big ball. Big ball doesn't move much, small ball has almost as much energy as it started with. But when the two objects have essentially the same mass, one could easily stop the other from moving, which is what would happen if the hydrogen wasn't moving thermally. So instead of stopping the neutrons altogether, it brings their speed down to a distribution that's associated with the moderator's temperature, before some of those neutrons escape from the surface. So from orbit, if you measure the number of fast neutrons versus thermal or almost thermal neutrons, you can get an idea of how much hydrogen is present a meter into the surface of the planet, planetoid, or moon in question. But it doesn't stop there, because nuclei can get excited when they absorb or collide with neutrons. And once nuclei are excited, they will quickly return to their ground state by emitting gamma rays. And remember, the energy of the photon is the difference in energy between the energy states of the nucleus, which means you get a different signal for different elements. And sure, you could send a lander and dig half a meter, but by being able to do these measurements from orbit, you can collect data over an entire planet. And it's all thanks to our understanding of those little weird bits that lie at the center of everything.